This is the lecture for April 8, and in this I'm going to solve problems from chapter 19. This is the chapter on thermal properties, and in particular I've picked problems that I think that span across the book, because I think that the thermal property chapter does a very good job of integrating concepts in material science. So the first problem we're going to solve is problem 19.3, and this question is asked to determine the room temperature heat capacities at constant pressure for copper, iron, gold, and nickel. So this is heat capacity. Heat capacity is joule per mole K. And kind of the purpose of this problem is to get you to recognize and to work with heat capacity versus specific heat. So your textbook in table 19.1, they give specific heats, CP, little cp, and little cp is in units of joule per kilogram Kelvin. And we're looking for big CP, which is joule per mole Kelvin. So basically, we have to convert between these, and if we have, we want joule per mole K, and we have joule per kilogram K, we need to get rid of the kilogram, and for that we need the molecular weight of copper, iron, gold, and nickel, which we can get from a table in your textbook. So that's going to be Cp is equal to Cp A, I'm going to all X for whatever the element is. So that's going to be gram per mole, and then we have to have 1 kilogram per 1,000 grams. And doing that, we wind up with joule per mole K. And looking these up, we wind up with Cu, Fe, Au, and I, with heat capacities of 24.5, 25.0, 25.2, 26.0. And these are all joule per mole K. And part B of this problem says, how do they compare and how do you explain this? Well, they are all about the same. They're approximately the same, and the reason they're approximately the same is, for one, they are all at a relatively high temperature, and I don't know if I call it high temperature. Let's say they are at temperatures above the Debye temperature. And if you're above the Debye temperature, what that means is it means that all of the processes for storing energy are activated, all of the lattice vibrations and the electronic contributions. Another thing is that copper, iron, gold, and nickel, they are all good electrical conductors, which means that the number of states available near the Fermi level are all relatively high for all of them. If instead of, say, nickel, we put in something such as, say, tungsten, which is not a good electrical conductor, then you might see some variation, and you'd have probably a lower heat capacity. But here, these are all good electrical conductors, and they're all at temperatures above the Debye temperature, meaning that you should have all the processes active. So that explains why in the table these all have about the same value. So next we're going to look at problem 19.4. And this says for copper, the heat capacity at constant volume at 20 K is given at 0.38 joule per mole Kelvin, and the Dubai temperature is 340 K. Estimate the specific heat at 40 and at 400 K. So, 40 K, that is low temperature. And at low temperature, we know that these heat capacity curves look like this. At high temperature, it's around or above the Dubai temperature. It's around constant, and around constant, it's around 3R, the gas constant, which is a pretty good approximation at high temperature. And at low temperature, the curve goes as proportional to T to the third. And in particular, we'll write it out as just having some constant of proportionality is equal to A T to the 3. So in order for us to describe the low temperature range, we need to find A. And that's why we were given the heat capacity for a particular temperature at low temperature. I mean, if they gave it at high temperature, we'd have a hard time actually trusting our interpolation or extrapolation. So we've got A is equal to CV, sorry, A is equal to CV over T to the 3 is equal to 0.38 over 20 to the 3. A is equal to 4.75 times 10 to the minus 5 joule per mole K to the 4th, which means that now we can go back and say CV is equal to A T to the 3 and substitute in that and substitute in 4AK, which gives us a heat capacity of 3.04 joule per mole K. And then up here in the high temperature limit, where we have around 3R, we have T K CV is approximately 3R is equal to 24.9 joule per mole K. Which is again all kind of in the same range for a good conductor. Now, oops. I'll take a step back here. I should point out this is heat capacity. We're looking for specific heat, which means that we then have to go on and say that CV is equal to CVA, or CV is equal to excuse me, CV over, call this ACU, CU, so that's the atomic mass. So this is going to be joule per mole K divided by gram per mole. So the moles will cancel out. And then we have to get rid of grams by having 1,000 gram per 1 kilogram. So now we have joule per kilogram K. In the case of copper, of course, this is 63.55 gram per mole, which ultimately gives us CV is equal to 392 joule per kilogram K for the specific heat. Okay, now problem 19.5. Problem 19.5 tells us that in our equation, CV is equal to AT to the 3, that A is approximately 12 pi to the 4th R divided by 5 Debye constant raised to the 3rd. And we're asked to estimate the Debye constant, the Debye temperature, given a specific heat of 4.6 joule per kilogram K at 15 K. So that means that we have to convert specific heat to heat capacity. Once we have heat capacity, we can determine A, and once we have A, then we can determine the Debye temperature. Okay, so CV is equal to CVA, and this is what we're looking at. Aluminum, so AL times 1 kilogram per 1,000 gram, because this is in gram per mole. And using that, we get, and this is the atomic weight, 26.98. That'll give us the heat capacity, and let's substitute that into this as well to get A is equal to T to the 3 over CV, T to the 3 over little CV AL, or 1,000. Oh, sorry, there's one. Small error there, which means now that A is equal to CV AL 1 over 1,000 over T to the 3 is equal to 12 pi to the 4th R over 5 Debye temperature to the 3rd. So now we have the specific heat, we have the atomic mass, We've got a conversion factor. We've got that. We're given 15K. We've got 12 pi. We've got the gas constant. We've got 5. So we're trying to find the Debye temperature. And doing a little bit of math, what comes out is theta Debye is equal to 375K. Okay. So those problems we're focusing on heat capacity and specific heat. Here's a problem looking at thermal coefficient of expansion. So we say we've got a copper wire that is 15 meters long, and we cool it from 40C to minus 9C. This is problem 19.7. How much change in length does it experience? So we're using delta L over L0 is equal to alpha L delta T, which means delta L is equal to L0 alpha L delta T. And this delta T is the final minus the initial. So in this problem, L0 is 15 meters. The final temperature is minus 9C, which we convert to, well, we don't have to convert in Kelvin because we're making the difference here. T0 is 40. Alpha L is from table 19.1, which this is for copper. For copper, alpha L is equal to 17.0 times 10 to the minus 6 inverse degrees Celsius. So we've got all of this, therefore we can find delta L is minus 12.5 millimeter. Okay,